Hey, welcome guys. So yeah, this video let's talk about the so-called orthogonality. Yeah, if you're working in a group representation, then most of people like to talk about the important property of the group irreducible representation is so-called orthogonality. Yeah, so yeah, we will prove these two. So these two are called the row orthogonality, which is easier to prove once you know the Schur's lemma. And another difficult part is the maybe in the next video we will talk about so-called Cullen orthogonality, which is much difficult. Okay, so let's go back to our list. Yeah, so in the previously let me just still talk about the logic flow, right? So in the study the finite group rep. So in the finite group rep, you first use the theorem, right? I forget the name, which we just proved in the previous video to say that the results basically every finite rep finite representation is a direct sum of the so-called irreducible rep. Okay, so in order to prove it, you need to use the property of finite and then construct so-called G invariant inner products. And then once you have this, you know that study the finite group representation, just study a reducible one. So in order to study the so-called irreducible one, then we have the Schur's lemma, where we just prove it. So Schur's lemma is not difficult. Just say that if you have two irreducible rep, and then there is a so-called G linear map, and if there are not, the F is isomorphic, or F is 0. And the second is that in a complex case that F will be lambda times identity for some lambda, if they are the same. Okay, so which just tell you that if two, so from here that you just notice that if two rep, okay, if two E rep are different, so that means they can be the same vector space, right? But different group representation, then the only linear map from V to W, G linear map from V to W is 0. And if two rep, E rep are the same, then the only linear map from V to W is some lambda times identity. Okay, so some people will write some notation say that if you have two rep, you talk about homomorphism from V to W. So this is not just a linear map from V to W, but so-called G linear map. So some people will use this notation to denote all the G linear map from V to W. Okay, also some people will talk about so-called group algebra. So yeah, I just want to talk a definition because I think we will not use it. So group algebra means just all the function f from G to complex number. Okay. And you can also talk about the G module. G module. This is just some notation that we will not use it, but in a group representation, some people use group algebra or G module to study. So it will make the study actually much more powerful if you know this language. But in order to prove the orthogonality, we don't need this. So G module means that right. So if you have group G, then you can construct a vector space, right? So each vector space denoted by element of G with the complex coefficient. So you can define your G to be span of G1, G2. So you just view each G as a vector space, as a basis. So all the element looks like summation Ci Gi, where Ci is basically complex. Okay, and then you can so this is vector space by usual summation, right? And so there's no group structure here, but for any element, if you act on GV, then you can define to be this, right? So GGI, right? So now this becomes another element. And so this will make this vector space. This vector space is an abelian group, right? And this G looks like a ring, although it's not necessarily commutative. So this makes this whole structure become a G module. Okay, so some stupid, some not necessary notation. Okay. Okay, so let's talk about the group the orthogonality relation. Okay, so orthogonality relation. This is orthogonality relation. of group irrep. I think in the chemistry that the people just believe that this is. People just talk that they told that this is true, right? But now we have Schur's lemma, so we should prove. Okay, so finally remark: if you have two linear map from V1, V2 that two are irreducible representation, then if V1 not the same as V2, then only map T0. If V1 is the same as V2 as the same group representation, irreducible representation. So yeah, both these are irrep. So irrep V1, irrep V2, V1, then this T will be complex number. Okay. Yeah, so this is in okay, maybe in the future I will talk about so-called simple objects, and I will make whole the group representation, make all the group representation as a symmetric fusion category. Okay, so let's prove the orthogonality. So in order to prove orthogonality, should be very simple. So let's consider a linear map. So consider any linear map H from V1 to V2. And let's define T to be 1 over G. G belongs to G. Rho to H inverse T H. Rho 1 G. This is G. Okay, so this is rho 2. So right, you have rho 1 and rho 2 because 2 irrep. So 1 G inverse H rho 1 G, and the sum over G 1 over G T. Okay. So your exercise for you is to easily check that the T is this T is G linear. Okay, so I think it's very simple. Hope you guys can see, because now you can rho 2H inverse T rho 1H, right? So let's see. So if you sandwich this by rho 1H and sandwich this by rho 2H inverse, then you can combine, right? So it makes the same as your original T. So which does tell you that the rho 2H T will be T rho 1H, right? So which tell you that T is a G linear. Okay, so that means T, for my definition, has this, right? Looks like this, right? So this T can only have two consequences. The first consequence is that if they are not the same, then T should be 0, right? And the second consequence is that if they are the same, okay, so if they are not, if they are the same, then what can we say? Okay, so actually if they are the same, one can say T is 1 over n and the trace of H times identity n. So where n is a dimension of V. Okay. I think this is trivial, and how about this? So Chris quickly proof. Yeah, so notice we just take the T, right? Trace of T. So notice that I think everyone knows about linear algebra, right? So S inverse A, well, S inverse A as trace will be A. Okay, so you just take a trace, So you take trace of this, right? You get the trace of right. Right, but now these are all the same, right? So I basically in this case, rho 2 just rho 1, right? So these two will cancel, right, by this lemma. So it becomes 1 over G, G from G to G, and the trace of H, right? So this trace is just constant, right? So this is just trace H. So your trace T will be trace your trace T, right, will be trace H, right? So trace T will be trace H, and T is lambda times identity by Schur's lemma. So that means lambda is 1 over n trace H, right? So which make this, you go back to this one, your T, yes. So now your T become 1 over n trace H identity, right? So T become 1 over n trace H identity, right? By just put lambda, because T is lambda times identity. So lambda is just this. Okay, yeah, so we just prove it. Okay, so yeah, so why just go back to our list. So we got these two, right? So either T is 0, either T is this. Okay, so now we can prove the orthogonality. Okay, so let's say your row 1G is written as matrix. Let's call it A. It's basically let's write AIJG. It's just notation, okay? And the H is called HIJ. This is just matrix, and the row 2G is called B, BIJG, okay? And the row 2G inverse is basically B transpose and take conjugates. So basically it's BJIG. Okay, so why is this? Why this is true? Right? Because actually we are using the fact that row 2 and G is unitary. Okay, so this is the your work to prove it. So let's tell why this is true. Because in the finite group case, this row 2G times the group order will be identity, right? So actually this row 2G are diagonalizable, right? So row 2G, you can prove that in your linear algebra case that if you have a matrix which up to some power will be identity matrix, then your row 2G this matrix must be diagonalizable, right? So that means it is the basis such that row 2G looks like this, right? But if G is identity, you go to G's identity, that means all these eigenvalue are roots of unity. So lambda is roots of unity, right? And so if you change it back, then you take conjugates and times it, they become identity. Yeah, because it's roots of unity, so that means lambda I inverse will be lambda I bar. Okay, so from here that you can know that the group representation in the finite group can always choose to be unitary. Although it's not so trivial, but it's not important. Yeah, you can just believe what I'm just saying. And this is the sketch. Okay, so right from here we have this notation. Okay, so now go back to our results, right? So T is here, right? So obviously that since H is for arbitrary H, if they are for arbitrary H, this T will be 0, right? So I can choose H to be identity. Okay, so which just tell you that if V1 is not the same as V2, then you immediately have this 1 over G, sum over G to belongs to G. This BSI G, ATJG is 0, right? Because they just write down everything, right? Just change the notation as this, and then change the notation as well. I mean, however, T and S are just some notation. I and J are just another notation, because you just write this as the product matrix, right? So you just write down the matrix inverse, and you know this, and H pick up identity in row 1, right? So this equation actually is very powerful because it gave you 4 identities, right? So for all S, I, T, and J, this is the orthogonality relation. Okay, if V1 and V2 are not the same. Okay, so in case that so second case is in case that V1 and V2 are all the same as V, then we can do the same thing, right, for any H. So let's pick out H to be identity. Oh, by the way, so I think okay, so for any H, so that means we get the trace H identity from 1 over G. G belongs to G, ASI G, ATJ G. Sorry, this is there should be HST, right? So this is just write down everything, and we got this, and H is arbitrary, right? So I can pick H to be identity. So you immediately get 2 equations, right? One is the 1 over G, sum over G, AJIG, AJIG. Right? If you pick up the diagonal term, if we pick out the diagonal term, then we pick H to be identity. So in order to non-zero that the S must be the same as T, right? So you can change your notation, it become 1 over N, okay? And then 1 over G, G belongs to G, ASI bar G, ATJG is 0 if S not the same as T, or I not the same as j. Okay, so this means that if these two are different, or these two are different, then this will be 0. And if they're all the same, then just 1 over n. So this is just easy. You just choose HST to be diagonal, right? So to be identity, so S must be the same as T. So it will fix these two. Okay, and yeah, right. So you just choose S and 2T to be the same. And then you will fix these two, but the left-hand side is still another identity, right? So this is double identity. So if you this need to be non-zero, that another term, this your JI, these two indices must be the same, and this SI and TJ must be 0. If one of them is non-zero. Okay, so this is also orthogonality. Okay, so maybe it's not hopefully maybe it's not obviously this all the results. But if you see that this is just exactly this relation, right? Because this is I1, J1, I2, J2. Forget about conjugates. They are the same if they are all 0 if they're different representation. And there are another two delta function, which is just the first one index, the first two I1, I2 indices, J1, J2 indices, and the times the factor, right? So this factor just switch the G divided by dimension. So which this is just a okay, so this relation is exactly three relation that I just proved. Okay. Yeah, so this is just so okay, so you can combine this one and these two, and finally you get you can just go to the Wikipedia or something, and you get a so-called combine the 1 to 3, you get this so-called row orthogonality. Okay. Okay, so let's yeah, so this finished the row orthogonality proof. So proof just using the Schur's lemma and play around with some indices. Okay. Okay, so next let me just talk about a character. Okay, so character is a very important idea, probably the most important in the group representation. And so the character, I will leave some detail into the next video. Okay, so this is just a quick definition. So before we start, let's define a so-called inner products. Let's define inner products on C of G. Yeah, so or some people use C of G. Okay, so this means just the notation, just a function from G to complex number. Okay, let's define inner products. Let's say phi and psi. Inner product denoted 1 over G, and phi of G, psi of G. G belongs to G. Okay, so maybe this will not necessary. It looks not obvious, right? But if you learn about the Fourier analysis, hopefully this makes you feel comfortable. Okay, so from this notation, we can get our previous results become Aij, BKL, right? Is 0, right? This is the first orthogonality iteration. And also Aij, AKL will be what? 1 over dimension of the V, or basically I use N, and delta Ik, delta JL. Okay. This is the orthogonality of the irrep. Okay. So now we talk about character. So character is the key idea in a group representation. So for given a group representation, right? So I define X row, which is some people talk about in writing as SV, but I use S row. So X row act on the G. Sometimes I use SV, right? So I just tell you my notation. So X row G defined to be the trace. There is each G map to a group, right? So the trace what? A row G. Okay. So obviously this is just all the eigenvalue of this trace. Yeah, so this is just the character. Okay, so obviously character is a class function. So it's a class function. Okay, so class function means that the X row G will the same as X row H G H inverse, right? This is from trace. Okay, so theorem. This is how we got to prove in another relation, so-called if two complex irreducible representation, if they are irreducible, if they are the same, there will be 1, otherwise there will be 0. So this is the orthogonality translation from the grant Schur orthogonality or row orthogonality to the character of the orthogonality. Okay, so this is the me part in the group representation. Okay, so what I going to show is that x row 1, row 2 is 0 if they are not the same rep, and the x row 1 and row 1 is 1 if they are the same rep. They are the same e rep. Yeah, so up to now, so from now we just always this orthogonality and these results also just works for the irreducible representation. Okay, so this should be diffused as exercise because not difficult. But that's so I only prove this, right? So this is easy because this is 0, so you can check by yourself. Yeah, so let's see what's going on. So x row 1 is what? Right. So x row 1. That's the x row 1 G, right? What is x row 1 G? Should be what? A from my notation, right? So let's say row 1 is A, so I just use AIIG, right? So row 1 G will be AIIG, right? But it's trace, right? So I should what? I sum over I, right? Because trace. And what about yeah? So we can prove by definition, right? This guy is just 1 over G summation G belongs to G, summation I G, summation J G, right? And what? And what? So now I shifted. There are 3 sum, right? But now all these are finite, so I can shift it. I can just change the order, so I get 1 over G IJ G belongs to G A J, right? And by the orthogonality relation, this is sigma delta ij, right? So the only case this knowing non-trivial is ij equals I, right? And by the way, there is a factor here, right? So the factor is 1 over G divided by N, right? So it's so this is G divided by N. Okay, so let me just write down everything. So let me just, so it's delta AI I. I guess let's see. Sorry, there should be complex conjugates here. So it's here, right? So we can still, yeah, we just use the orthogonality and the sum over G. So this guy by the orthogonality relation will be 1 over G delta ij, and the G divided by N. Right? So N is the dimension of the representation. So this GG cancel, you get the delta ij square 1 over N, right? So this is trivial. Only I belongs to J is will not cancel, right? Only I belongs to J will become 1. So it's 1 over N times N, which is 1, right? Because how this is I is just from 1 to N, which N is a dimension of representation. The dimension of irreducible representation, okay? Okay, so we prove this. Okay, so you can use the same orthogonality relation, right, to prove this. Now it's trivial because A is not the same. If A is BJJ, it becomes 0, right? Times it becomes 0. Okay. Okay. Yeah, so what we prove is that for 2 irrep, their character are orthogonal. So let me just write down the words 2 irrep. They are orthogonal. They are also normal. So basically, their character are also normal. Their character, so that we get x row I and the row j, which become delta ij, right? So very beautiful relation if row are the irreducible representation. Okay, so let's talk about the consequence. Okay, so the consequence is that suppose you have suppose given any representation, you have a decomposed, let's say v1 in the direction a1, direction sorry v1. So v1 a1 means bad notation. So v is a v1. A1 means v1 direction a1 means that v1 direction v1 direction v1 a1 times, and the direction v2 direction a2 times, direction v3 a3 times. Okay, so suppose you have a representation, and you can ask about xv. right? So which xv is just the character, but this is block diagonal, right? So this xv just sigma ai x I, right? Or basically rho I, but now I just use I, right? So this v1, v2, and the vn are irreducible one, okay? And you can easily check so since they are orthogonal, right? So the inner product of these two will become a summation I ai square. Notice that these ai are all integer, right? So there's no complex value we need to, there's no other detail, right? We just make some ai squared. Okay, so this is the first notation. The first results, okay? And also, yeah, so this is the first results that we just say. And the second result is that if two representations are the same, they should have the same character, right? Because we already proved that if the two representations are the same, that means there is a basis change P, which is invertible such that any rho 1G is the same as P inverse rho 2GP, right? So if you take the character, they become the same because you take a trace. So if they are the same, their character are the same. Their character are the same. Okay, so that means in general, your SVXV will be summation AI squared, right? So which tell you that if xi is irreducible, if only if xi is 1. Okay, so previously we just proved that if xi is irreducible, then xi inner product will be 1. But now I proved that if xi equals to 1, then it is irreducible. The reason is that since it's irreducible, so in the previous factorization, there's only one term will survive. So this is the proof. Okay. Okay, so the next thing that we will prove now is that this is the most important results. That the number of G, which is the order of G, will just be the dimension of all the irreducible dimension square, sum of dimension square of all the representation, irreducible representation. Okay, dimension bi squared. So where I is irrep. Irreducible rep. Okay, so from now on, I'm very lazy, so I denote G hat as all the irrep. The problem is that I didn't define I didn't provide any structure of G hat. I only say as a set. Okay. Okay. So this is the reason. So what is the consequence about this? So the consequence, the first is that obviously that the dimension of Vi, right, will for each one will less than square root of G, right? Obviously. And the second is that we just prove another fact that we haven't proven. The number of the irreducible representation of a finite group G is finite. So there are only finite irreducible representation. Okay, so quick example. So quick example is that if you take G to be S3, which is non-abelian and the order is 6, then you can write it as 1 squared plus 1 squared plus 2 squared. So which you can show that the S3 has one irreducible representation, and another dimension 2 irreducible representation. So once you have this, that somehow like you already get a lot of information. Okay, so our final results theorem G equals to this. Okay, so the proof we need to use the regular representation. So somehow maybe you guys already forget. So if you go from G to general linear group V, right? So regular representation means that this V choose to be the number of the basis of V, just to choose to be the group itself, the group element itself. So the dimension of V will just be G, okay? Right? So that means the regular representation just that you act on any group element H, right? You just permuted it. So let's I denoted this just by row. Right, so I mean I just denoted this by row because otherwise it's terrible. So I just using row G, and you know this is the regular representation. Okay, so regular in representation row row G and econ G, right? So now row G is a matrix from V to V, right? But now V looks as a span of the V as a user G as a basis, right? So row G econ EH. So EH is just a basis of the use H as a label, so become EGH, right? Just permute, okay? So we want to ask about what is the character of this row regular, right? Row regular, so row G. Okay, so obviously that if G is identity, right? So let's talking about trace. Okay, so if G is identity, then it should be trivial, right? If row G is identity, then row is identity, right? So the trace is just the G. And obviously that if G is non-identity, then somehow like if G is non-identity, right? Then the row G econ EH will become EGH. And then there's no, so if G is non-identity, then GH will not the same as H, right? So when you write your row for G non-identity, then it becomes their diagonal term must be 0. And then there will be one here, something. So this will be 0. Okay. So hope you guys can see this. Okay. So this is a character, right? So the character of this row will be G if G is identity. If G is non-identity, this becomes 0. Okay, so now we can use our results. So our original results prove that X row will be sum over decompose, right? So sum over decompose, which is AI squared, right? If yeah, with sum over S, there's sum over AI squared in the decompose. Okay, so and also each AI, right? So each AI is what? Each AI is just the oh yeah. So just yeah. Okay. So let's maybe take a step and step back. Okay. So from this, right, we got this, and we also get this AI, right? It's just XV econ XI, right? So easy to see, right? Because these are also normal, right? So XV XI will be AI. Okay. So this guy can also be written as I from G hat and X row XI. So I need to count how many multiplicities in terms of these, right? So this is, by the way, this is just an right. So just yeah. Okay. Okay. So let's working on this. Okay. So now this become trivial, right? Because this is 1 over G. Summation G belongs to G, X row G, and the XI bar G. Okay, so but I just proved that the G only identity is non-zero, right? The only non-zero is identity. So this guy is just 1 over G, and the G is identity, so it's X row identity times XI identity complement. Okay, so X row identity is what? It's G, right? So it's G. So it's 1 over G. And then what is XI identity? So XI, anything econ identity, right? So XI identity, so this XI is a representation. So any representation at identity, it's just identity. But you take trace, right? So it becomes a dimension of that representation, right? So it's dimension VI. So that means in a regular representation, each irreducible representation happens at its dimensional times. Okay, so now this is AI. So AI is the same as dimension VI. Then you go back to here. So we just proved that our final results. So you take how many I belongs to irreducible representation, and then the dimension of VI squared. This is the integer. Okay, so just go back to our example. So our example is S3, right? So the G is S3 is 6, right? So 6 can be written as 1 squared plus 2 squared plus 1 squared. So which tell you that S3 has one irreducible rep with dimension 1, and the one E-rep with dimension 1, and the one E-rep with dimension 2. And what we just proved is that if you work in a regular representation of S3, this representation, right? This representation can be decomposed into the let's say U is the one-dimensional representation 1 times, and the direct on another U1, U2, another, this is 1 dimension. This is 1 dimension. And the direct on another U3, which is a 2 dimension but multiple twice. So let me just say final times. First, let's say again. So the regular representation can be decomposed into the irreducible representation, and each irreducible representations always happens its dimensional time, because this is dimensional 2, so it happens twice. So this is what we just proved by using the orthogonality. Okay, so in this video we prove the row orthogonality and introduce a character. In the next video we prove the column orthogonality, and then we will prove another theorem, which is a very non-trivial. It's the number of irreducible representation, a number of the irreducible representation of a finite group G, the same as the number of conjugacy class, the number of the conjugate class. Okay, so this is our next goal. Okay, so once we finish all this, then we can start compute the real examples. See you guys.